Hello everyone, good evening. I will be presenting Scalable Light Field Coding or SLFC. My name is Hadi. I will briefly introduce myself. I was working as an embedded system engineer for a while. We were designing and implementing an automated dispensing system. Then I decided to move to research. Then I joined EMRG project. We were working on emerging image modalities, their compression and representation. And then I moved to Austria and I joined Athena. In Athena, which stands for Adaptive Streaming over HTTP and Emerging Networked Multimedia Services, we are working on content provisioning, content delivery, content consumption, and end-to-end aspects of video streaming. And our industry partner is Bitmovie. So let's go back to our talk. I will briefly introduce light field imaging and then I will talk about light field compression. I will introduce SLFC followed by some experimental results, and finally I will conclude this presentation. As you know, immersive technologies try to imitate the physical world through digital simulation. And as a part of immersive technology, 3D photography aims to enhance the user experience by reproducing a light field that emerged to form a real scene. Initial attempts is back to stereo imaging. Two offset images were taken and they were presented separated to our left and right eyes. And stereo displays mainly were using glasses-based procedure to create the impression of depths. Despite providing the impression of depth, stereo displays were introducing viewing discomforts. And like we had fatigue, we have eye strain and headache, and we were suffering from unnatural viewing conditions. To address all of these challenges, new imaging modalities were introduced: light field, point cloud, and holography. There are some ongoing researches on these topics. For example, there is an activity in JPEG. They were working on static images. So their activity is called JPEG Plano. They try to provide a standard framework to compress and represent these image modalities. And in MPEG-I, they were trying to solve encoding and representation problems for light fields and point clouds. So let's see how light field photography works. All of these modalities comes from planoptic function. Planoptic function is a 7-dimensional function that is used to model all light rates at every possible location, at every possible angle, at any time, over any range of wavelengths. Then we will have a 7-dimensional planoptic function, which is quite complex to be processed. Then simplification is needed. Therefore, light rays are assumed to be time invariant and monochromatic. Therefore, 2 dimensions are removed, which are t or time and lambda. Then it is assumed that light rays are traveling in a free space. Therefore, our 7-dimensional function will be simplified to 4D function. 2 planes are used to model this 4D function. They are recording all the light rays that are traveling between these two planes, and the output would be multi-view images, as you can see here. So, unlike the conventional cameras that can only record 2D light intensity, light field cameras can capture both directional information and intensity of the light. We will be able to record spatial information in addition to the angular information, while in the conventional camera it is only the spatial information that is recorded. We will have a very complex setup for this. A multi-array camera is used to capture a light field. So the output would be multi-view of the same scene. But there is some commercial cameras like Light Raw camera that has some built-in macro lenses inside that can generate this multi-view images. In any case, we will have multiple views of the same scene. By capturing these multi-views of the same scene and processing these multi-views, we will have light field volume. And it will enable some post-processing tasks like refocusing, changing viewport, depth estimation, 3D modeling, and synthesizing new views, and they will enhance the user experience. This is one example that the focus has been changed in these three images. For example, here the focus is on this face, but in this figure the focus is on this face, and in the right one the focus is in this face. Or we can change the viewport after capturing the light fields. Here is one example. On the right image, you can see that the viewport is changes. And on the left, it is the focus of the figure that's changing. So all in all, the user experience will be enhanced using the light fields. But at the same time, we will face with some new challenges. As you know, the main challenge comes from compression side, because unlike 2D images that we have only one image, here we will have multiple images that should be encoded. Conventional methods usually convert all of these image views into a pseudo sequence, and then they use a video encoder to compress this pseudo video, and then the generated bit stream can be decoded, and these views can be reordered again to create our multiple views. But here we see that the dependency between the views will be increased if we are going to intercode all of these views. And it will bring us some new challenges. Most of the works in the literature try to improve encoding efficiency, but there are some other features that should be considered when we are encoding the light fields. There are viewport scalability, quality scalability, random access, and uniform quality distribution. So why we need viewport scalability? In order to increase compatibility with our display, capturing device, network condition, processing power, and storage capacity. Imagine that we have a regular 2D display. So we will need only the most central view. But due to the dependency that there exists between different views, we will need to transmit all the bit stream and decode all the bit stream to have access to the arbitrary view. For example, here, if we want to have access to most central view, which is here in our bit stream, due to the dependency, we will need to decode lots of views to have access to that view. While our display is a regular 2D display, and we only need to have access to the most central view. The other important feature is quality scalability, very similar to video scalability. In order to increase compatibility with network condition, processing power, and storage capacity, it's necessary to provide quality scalability in light field imaging. The other very important feature is random access. As you see, we always need to navigate between different views. So when we navigate between views, if the dependency between different views is high, then we will have a high decoding delay. When we are streaming the light fields, we will require high bandwidth and very high processing power. So, and in this example, imagine we want to navigate between the top left view and bottom right view. And because of the raster or snake dependency that there exists between views, we need to decode all the views in order to have access to the last view. As I mentioned, it will increase the decoding delay, bandwidth, and processing power. So, on the other hand, when we want to render light field images, if we provide the random access, we will need less memory footprint. Otherwise, we need to export all of the bit stream to to the memory, which will make some problems for rendering the lightful images. So random access is also very important to decrease the memory footprint. The other important feature is quality distribution. Some methods do not consider this very important feature, but when we navigate between different views, we can see that it's not good to have different quality levels. So as you can see, we need a uniform quality distribution between different viewports. Based on all of these challenges that I introduced, we introduced SLFC or Scalable Light Field Coding. In SLFC, all the views are divided into different 7 layers. So as you can see here from layer 1 to layer 7, in each layer, red view belongs to that layer. For example, here, this red view belongs to layer 1. In the second layer, corner views that are represented by red belong to layer 2. Gray levels belong to the previous layers. For example, here, this gray view belong to the previous layer or the first layer, and black views belong to the next layers. Based on this division, for encoding the different layers, the most central view is intra-coded. As I mentioned, nowadays we mainly have 2-dimensional regular displays. So we intra-code the most central view, then it can be independently accessed. So we don't need to have access to the views in other layers. We can independently decode this view and have access to the most central. Then we use this view as a reference to encode 4 corner views. And we see encoding of the remaining views as view or frame interpolation problem. This is one example. Imagine that the most right view is our target view, and we want to intercode this view. We use the top right view and bottom right view as inputs for a deep neural network. In this case, deep neural network is used to interpolate the view. So if we use top right and bottom right view, we are going to interpolate the most right view. And here we can see the residual that there exists between target view and the references that we use for interpolation and the synthesized view. As you can see, the synthesized view has much less entropy information compared to the top right and bottom right view, which means that if we use the synthesized view as a reference, encoding efficiency will be increased. So for this purpose, we use SEPCON, video frame interpolation by adaptive separable convolution. And then we have our procedure as below. In each layer, which I mean from 3 to 7, 2 views from the previously encoded layers are used to synthesize their intermediate view. When the intermediate view is synthesized, it is added as a virtual reference frame to the reference list in the video encoder. Then to encode each intermediate view, 4 references are used for intercoding. Always the most central view, 2 views that are used for interpolation, and the synthesized view. In this example, when we want to intercode the most right view, we always use the most central view, top right and bottom right views that were used for interpolation, and the synthesized view. So these 4 references are used for intercoding. For example, if we want to do intercoding for this one, because top left and bottom left views are used to interpolate this one, then the most central view, top left, bottom left, and the synthesized view were used as references to intercode the left view. So here we can see the encoding efficiency for our proposed method, and when we compare it to the best competitor, which is PSP, you can see the name of the anchors that I use here for comparison. Our proposed method can achieve up to 45% bitrate reduction compared to its best competitor. But in addition to high encoding efficiency, we provide viewport scalability. The bitrate required to have access to views inside each layer is shown in this plot. You can see, for example, if we want to have access in Greek light field image, if we want to have access to views inside, for example, layer 4, then we will need 0.3 bit per pixel instead of forwarding or decoding all the views on all the layers. So in this way, we provide viewport scalability that based on our need, we will transmit the layers that are needed. Then when we synthesize intermediate view, actually we have one quality layer. But when we do intercoding to enhance its quality using 4 references that are introduced, actually we will have additional bitrate and then we will have the second layer. So we interpret this as a quality scalability. If we do only video interpolation, we will have the first quality layer. But if we do intercoding using the references, then we will have the second quality layer. Our codec provides a very good random access. Random access has a metric in JPEG Plano, so which is called random access penalty, which is introduced as total amount of encoded bits required to access a view divided by total amount of encoded bits to decode the full light. For example, as you can see here, when we want to have access to the most central view, we need only 4% of total light field. But for example, when we want to have access to the corner views, we will need only 6% of total light field. And at the worst case, we will need only 25%. So our codec is much better than pseudo-sequence-based methods that require all the light field to be decoded. SLFC provide uniform quality distribution. This is one example. This is heat map, PSNR heat map for Greek light field. You can see that the PSNR for all views is around 36 dB, which shows that the quality uniformly distributed between different views of the light field. But for future work, I'm trying to add spatial scalability. So I will have 2 layers, 2 resolutions. The first resolution, again, I will have the SLFC, the same procedure that I introduced. Then I will try to use the super resolution to enlarge or to super resolve the view images to their original resolution. And finally, I will conclude this presentation. SLFC utilizes a deep neural network to synthesize intermediate views. Synthesized views are used as virtual references for intercoding, and SLFC provides not only high encoding efficiency, but viewport scalability, quality scalability, random access, and uniform quality distribution. Thank you very much for your attention. If you have any questions, I would be happy to answer them.